the University of Washington Computer Science and Engineering Distinguished Lecture Series.
It's really an immense pleasure to host Bob Colwell for a distinguished lecture. So I know many of you know Bob, but I thought I would say a few words. So Bob was an office director at DARPA most recently, but before he was an Intel fellow, and he was the chief architect for many of our favorite chips, and probably chips are still running some of your machines here. So he had a very notable career. He had an Acramockley Award, which is essentially the top award in computer architecture. And the citation, the way I read it, is like getting things to actually work, right? So that's what your citation is, was getting great ideas and making them work. So he's also a member of the National Academy of Engineering and did amazing things. And he's a fantastic writer. He had this column in a Triple E computer called At Random that was going on at the time I was in grad school. It was really, really a highlight. Really, thanks for writing that. And a great book also that I recommend to my computer architecture students called The Pentium Chronicles, which has this really interesting mix of the technical story as well as the team stories behind it. And on top of it all, apparently he's a very, very good acoustic guitar player from what I hear, right? So thank you. Thanks for coming.
Yeah, it's my pleasure. So thanks for inviting me to come here. I was told this was a really steep room. I guess my advice to the architect was if you have to tilt your speakers to that angle, you've got the angle wrong. It's like, I'm going to need neck surgery after this. For anyone that missed it, and I hope there's no one that did, the metaphor here is the elephant in the room. And the elephant in this particular room, I think, is that our computer systems aren't as good as people using them think they are. And that's the theme you're going to see the rest of this talk. I think people are starting to use our products in ways that should scare them and should scare us. And so you're going to, and possibly, I'm going to hint at some possible remedies at the tail end. Courtesy of Jeff Bokor from Berkeley, I gave a version of this talk back in, I guess, September. And at the end, he asked a question that had to do with, great, so you're saying everything's messed up and you want to fix it, but you didn't say who's going to pay for it. And I said, that's a fair criticism. I will try to address that a little bit better. So first of all, let's admit what works. I think we should be very proud in the computer industry of an awful lot of things that we've accomplished already. For example, this is a 1997 cartoon, and it says, this computer is very fast. It became outdated faster than any computer I've ever owned, which often felt true back in that era. I don't know if it's so true nowadays, but in any case, the machines are fast and they're cheap and they're low power, and they're still going to improve from what they are today, at least for a few more years. I'm one of those people that thinks Moore's law is either dead or going to die soon, and that means some fundamental things about what computers are going to be capable of in the future. For people that have grown up through the Moore's law era, and I did, and I think probably everybody here has, I think we're used to this feeling like, well, if we don't do anything and just wait around a couple years from now, things will be a whole lot better. And that's historically been true. My claim is it will not remain true, and there are some implications for that. One of the reasons I went to DARPA was to try to convince our high-tech military that this is one of the things they need to think about, is what they're going to do in a post-Moore's law era where they can't simply wait around for industry to give them faster stuff than the other side has. I'm not sure if I got through to them, but that was my intention. Here's some bad stuff. So we're really good at performance and we're good at cost. We've proven that, we the industry, have proven that over and over. But there's other aspects I don't think we're quite as good at. Now, the first thing I listed was system reliability. And if I were you, I'd be thinking, well, wait a minute, what are you saying? Our systems are unreliable? No, they're not. My laptop works all the time. That's true. In an isolated system-by-system basis, the things that we make have proven to be at least good enough for what we use them for. But we don't would you use your laptop or would you use your smartphone to control your car with you in it? I would not. I had more than one case, by the way, where I was presenting to Air Force generals, more than one equals two, where I was presenting to an Air Force general and about what's wrong with software, there's too many bugs, what are we going to do? And he whipped out his smartphone. Two different guys, both did the same thing. They whipped out their smartphone and said, see these apps? That's software. That's what I want. And I said, no, that is not what you want. You think you do, but you don't. If that's the software that controlled your airplanes, you would not survive more than 1 or 2 trips. It's not designed to the same level. You just don't see the difference. But it's there nonetheless. Other things, I think there are limits to our ability to actually design complex systems that we don't always admit. I loved it once. Like in 1994, I was in Australia when John Hennessy was talking about one of the MIPS chips. And he said we had to take some of the functionality out of that chip at the very last minute of the design of that machine because we had gotten in over our heads. We had too much complexity. We couldn't handle it. We had to back off. And I thought that is a very mature thing for an engineer to do, is to realize that they've not just hit that limit, but walked past it. Because you cannot walk past it because it will bite you. So you must back off to the level that you can handle and do that. And I see other systems that I think suffered from the reverse syndrome where people just kept going and you end up with this unholy mess that doesn't always do what you want. Logistical tales, I'll tell you about that in a minute. And the user interfaces in particular, I have a lot of disdain for in general. This is a Dilbert cartoon where Dilbert wants to delay the launch because the user interface is bad, and somebody says, when did you become a communist? Which is a way of saying, look, I want to make money at this thing. You haven't shown me yet that I won't make money even if I put it out there and users die. That's kind of more cynical than I want to be personally, but that's Dilbert, that's why it's funny. Here's the ugly part. So I'm going to define bug as behavior other than what was intended or expected. You probably have a better definition for people that work on this stuff, and I would love to learn it because I don't know what it is, but to me that's what a bug is. And I came up with this list of 14 things to worry about. It's not meant to be comprehensive. I literally sat there and just thought of a few and wrote them down. I'm sure I could double the length of it if I tried. And the point of it is, I think all of those sources of things that could go wrong need to be taken into account and thought about as we design systems. And I know we do some of them. For example, there are people at a place like Intel that worry about that particular thing really a lot. And they understand the physics of it and so on. But even in that context, I had a case once where it was about 1995 or so at Intel, and the packaging guys came to us and said, panic, emergency, for all future chips, the number of alpha particle hits you must handle correctly have now gone up by a factor of, I don't know what it was, 20. And I said, 20? I'm assuming that was the right number. 20 is going to, I'm going to have to triplicate my registers. I'm going to have to triplicate wires. What are you talking about? And they said, look, that's just the fact. You have to live with that. You have to fix this in the architecture because we can't fix it anywhere else. And so I left that meeting thinking, I hope he was wrong and gets inspired tonight to solve the problem the way silicon people normally do, which is they say, never mind, we fixed it. And then as an architect, I go, oh, dodged another one. And that is, by the way, what happened in this case. It turned out what they were doing is putting radioactive lids on the packages. Don't ask me why, but that's what they were doing. And so sure enough, a source of alpha particles that's that close to the silicon has a bad effect on the reliability. And when they stopped doing that, lo and behold, it stopped malfunctioning. But for a while there, I was thinking, oh, the time has finally come when the silicon has returned to the bad old days of unreliability of the 1950s. And now we have to start, as architects, saving the butts of the people that do the silicon. And that's going to be really costly and ugly. Fortunately, we dodged that bullet, and we're still there. But my point is, yes, there's people looking at it, but it's not a solved problem. It still matters, and in some cases, it matters more than others. And what I want to do is sort of list that there's a lot of places to worry about here. And incidentally, this is not theoretical. For instance, just recently, Intel found what they called a specialized TSX enterprise bug on the Haswell and Broadwell CPUs. I took that to mean something to do with cache coherence, but I don't know. I don't work there anymore. How about the Chernobyl nuclear plant? I think there was a combination of user interface errors, design flaws, built-in instability, training for the people that work there. There were a lot of issues there. How about user interface? This one says, remember that, what was the name of that stupid paperclip? There was a name for that little guy. Clippy. So here's Clippy saying, it appears you're trying to launch the space shuttle. Would you like some help? And here's two choices, enter stable orbit or slam into mountain. And I think, actually, you really shouldn't, Mr. Clippy, you shouldn't actually give them that choice. Nothing good can come of that. And by the way, lest you think that's totally made up, at one point, as a member of this ISAT group that Louise is part of, several years ago, we went to Nellis Air Force Base, and I saw the people flying the Predators, because that's where they fly them from, is the Air Force Base near that place. And we were watching them do this, and the same thing usually happens. The bosses that are trying to impress you with how great everything is, they're the ones doing all the talking. And behind you are all the enlisted people that actually do all the work, and they're muttering and laughing and making snide comments. So that's where the truth is. So while some of us were talking to the bosses, I was backing up to listen to what these guys were really saying. And at one point, I grabbed one of them and said, you appear to have reservations about the story being told to us. Would you care to elaborate? And he said, sure. Ask them what happens. How do you launch a Predator? You call on the phone and you tell the ground crew over in some other country, wheel this thing out, gas it up, put it on the runway, and then run away, because you're not controlling it, I am, and you don't want to be around if I screw it up. So they put it out there. And he said, so the first thing you do is you turn on a fan deep inside the machine, and you do that by pulling down menus and submenus and submenus, and you finally get to the one little thing you click on and it turns a fan on. And I said, all right, so what's wrong with that? Well, he said, well, that's boring, and you got to do that every single time you fly. So instead, you map all those submenus to function keys. Function 1, 2, 3. So you get used to, instead of thinking about turning the fan on, before you take off, you just go like this. Function 1, 2, 3 with your hand. You just go, dun-dun. And I went, okay, sounds a little funky, but whatever. And he said, ask yourself the question, what happens if you hit 2, 3, 4 instead by accident? And I said, okay, so enlighten me. He said, well, the plane powers up, turns left, runs into a concrete wall at full speed. And I said, I'm guessing this is not a theoretical concern. And he said, oh, no, not theoretical at all. That's user interface, right? Why is that possible is what I would ask the user interface designer. How about this one? The A400M airplane, a military airplane, was crashed because of a software bug in the engines. And do you know what the software bug was? Key files dictating torque response were deleted during software installation prior to the flight. Now, my question for you is, why the heck is it possible for that thing to leave the ground without a full complement of necessary software on board? How's that possible? Why did the people that wrote the software allow that to be possible? That just strikes me as a really bad design decision. In other words, I'm not pointing at the poor software person or the maintainer or whoever it was that accidentally deleted these files. Yeah, they screwed up and shouldn't have done that. But this is a design flaw. This should not have been possible. Someone in the software should check, is everybody here first before I take off? That's an obvious check that needs to be done. Okay, so our reach exceeds our grasp. Now, these are Google self-driving cars. I think they're marvelous things. I think it's really cool that humanity has come to the point where we can start trying to design things like this. That's the good news. The not so good news is I know what's in those things, and it's scary. I think it should be scary to you too as to what's in there and what they're using them for. I'm not saying that humans drive better. I'm not going down that path. I've seen too many humans drive. I think it's obvious that any machine is going to do a job of better than most human beings. Maybe not experts, but most people are not experts no matter what they think of their own driving. What I'm saying is that vision, the vision of sticking technology of the type that comes out of our industry, hardware and software, into those things and allowing lives to be based on that is a scary vision because of knowing what's in those things and the status of them. And we know that those assumptions are not true, whether those guys know it or not. So I think the right thing to do is to figure out how to make the assumptions become true, as opposed to convince them to just give up on some theoretical possibility someone will get hurt. That's not where I'm going with this. I actually think we can do a better job of making the assumptions that they're already making, let's make those become true. So there's a bunch of things you can do. Like immediate surprises means if you put a product in the world on the next day, what is it facing? If anything goes wrong, that's what I would call an immediate surprise. For example, there's design errata. If you put design errata in there, then they potentially manifest on the very first day. I personally like to split design errata into at least two important groups. One is reasonable bugs, meaning we could get together knowing the source of the bug and the etymology of the bug, and then we would look at each other and go, I don't think anyone is going to catch that. That's one of those bugs that's so subtle, so insidious, that it's really not reasonable to think people would see this no matter how much introspection they apply to the problem. I've seen bugs like that. I know they exist. So I'm saying that's one class of bugs. There's another one, which I would say is just bonehead stupidity. Like I think allowing the plane to leave the ground without all the software on board is potentially an example of bonehead stupidity in terms of the designer. And there's lots of other ones. Just to pick on myself, here's an example of a bonehead stupid thing that I did. When I was at Multiflow, I designed the floating point square rooter divider unit, which was it was on a card, a circuit card about this big, and the square rooter divider was about this much chips all taken together. So the level of integration was low. 4-bit slices was all there was, and so on. And so what I did, if you know the floating point, the IEEE floating point spec, the way you do floating divides and square roots is an iterative process, and you keep going through this loop where you generate a couple of bits of result each time through the loop. And at the end, you set the rounding bit, the guard bit, and there's a few other random things you do. And so what I did was, just so incidentally, you also have to set the exponent, because the mantissa and the exponent are two separate things. Now, looking back at this bug, it's entirely obvious what I did wrong. But here's what the bug was. A user came in, one of the other multi-flow people, and he said, it's really weird. I get the right answer out of your divider or your square rooter almost all the time, but I think it was the square rooter, actually. But when I take the square root of a particular number, like 3.99999, I get 1, not 2. And that doesn't seem right. And I said, yeah, that doesn't seem right. So I looked at it, and it turned out what I was doing was generating the bits of the mantissa, and if they're all 1s all the way across, and then I set the guard bit and the round bit, guess what should happen? I should go, oh, I have to adjust the exponent. And should I fail to do that, my result will be off by a factor of 2. Well, so I failed to do that in the first generation of the machine. And so the first thought that ran through my mind was, you know, they designed bridges to a factor of 10 over safety. It's 10x better than it needs to be. Guess how much the safety factor of an airplane wing is? 1.5x approximately, which is within the band of error I just created in my machine. And I already knew that these machines were going to be used by people in that field for designing things like airplanes. So it was quite the sobering realization that I almost inflicted on the world an airplane wing that was not, in fact, designed to 1.5x, but was designed to considerably less than that. And also now we have this hacks and attacks. Back in the day, in the 80s, I didn't have to worry about that too much as a designer. But if you're designing anything in the computer industry nowadays, no matter what it is, you have to take these things into account. There are human beings out there that wish you harm, and they want to attack your company, and they want to break your product. And if they can use the things you created to hurt anyone else, they'll do that too. That has to be the attitude, ugly though it is. And that's new as of, I don't know, a couple decades ago, but it wasn't always like that. And then I also think immediate surprises have to take into account the context and the environment. And we'll talk a little bit more about what I mean. I'm also not trying to show you a comprehensive taxonomy. I'm not actually showing, hey, here's a framework, and if you just think about all of it, I'm not going that far. I'm just using examples. I think it's disturbing how easy it is to find bugs. The two classic ones that come to mind are the Hindenburg and the Titanic, both of which, by the way, were being used in their intended context in the way they were intended at the time they faced this catastrophe. So in both cases, I'd say, I would like to talk to the design engineer and ask what the heck he was thinking when he made certain design decisions associated with how those two things were put together, basically. And we have plenty of examples of our own. They're just not as easy to see. Here's another immediate surprise. So I forgot what the source is for the dang thing, but I found this reference to a researcher who's trying to figure out how would you hack a self-driving car? And so the basic notion is the only thing that the controller inside that car knows is what its sensors are telling it at any given moment. It knows nothing else. It's equivalent to you only know things because of what your eyes and your ears and various senses are telling your brain. Well, this car only knows what its sensors are telling it. So every one of those sensors is in effect part of the attack surface of that machine, if you're thinking like a hacker. So now the question is, how can the hacker use all of those myriad inputs to that car to fool the car into thinking there's something there, or that there isn't something there when there really is, or that the road doesn't actually curve this way but goes that way over a cliff? I mean, whoever is designing these cars needs to have taken every one of those things plus many, many more into account, plus the underlying reliability of our hardware and our software that they're counting on as being perfect at all times. I submit to you that second of that two things should not be taken for granted the way it is. And my question is, hadn't we better find out the answer to this question before we go into huge mass production on self-driving cars? And by the way, I don't mean to be picking on self-driving cars. I just think they're the most obvious example of using technology in a way that could be a problem. There's plenty of others. We have embedded controllers everywhere, inside our car engines, for example. There's some ugly stories associated with those too that I don't have time to go into at the moment. Here's another example from, by the way, you're going to see a thread through this. I keep picking on examples that are not from the computer industry. And I'm not doing it because I think they're all so stupid and we're not. That's not really the issue. What I'm saying is there are lessons to be had from outside the computer industry that apply to us. And I think it's sometimes easier to see what the lesson is when it's not buried in the technical minutiae that we are so used to in the computer industry. Sometimes I think it's simpler to watch a blimp blow up and say, what does this mean to me, than to sort of dive into the latest cache coherence bug from somebody. So here's an example of 1975, where there was a nuclear plant at Browns Ferry. There was a technician who, you might find this hard to believe, wanted to find the source of some gas leaks, or not gas like explosive, but there was a wind in this room, and he wanted to sort of he wanted to stop the air leaks. So how would you find an air leak? You take a candle or something, your lighter, and go, wind's blowing that way. Well, it's not really such a good idea to do that in a control room of a nuclear plant, but he did. And not just that, he tracked it down to the wall, and the leak was somewhere in the wall, so he took his candle and he stuck it in there. And he went, oh, I see it now. But he lit all the insulation on fire, and it burned everything inside the wall, including the triplicated control wires to the nuke plant. So he should have gotten some award, I don't know. But what it ended up doing was it knocked out almost all the safety systems. There was a normal feed water, there was a core spray, there was a low pressure, there was isolation cooling. He knocked all 4 of those out, and then he also killed most of the instrumentation that the operators could have used to tell what the state of the plant was, which then they would know what to do with it. So whoever designed the plant had never anticipated someone sticking a lit flame inside the wall. And so in one sense, you could say, well, why would, I mean, there's got to be limits to what stupid people will do, right? I mean, if you're a designer, you can't, you got to stop somewhere. Yeah, maybe. But in this specific case, yes, I do think the guy who had the open flame was an idiot. But I also think that the designers and the builders needed to take into account why were the triplicated cables plus the instrumentation wires all so close together in the same wall so that one event could affect all of them. And this has happened more than once. The idea of the designer said, oh, I can't lose all these at once. I'm going to triplicate my thing. And then on paper, it will look as though I've got redundant control. But if the guy who implements it takes all the cables and runs them through the same conduit, now you don't have triplicated. It just looks like it's triplicated. So the guy who's implementing it needs to understand the intent of the designer. And I think it's the designer, it's incumbent on him or her to make sure that that's followed through. Long-term surprises. So by long-term, it's context dependent, but suppose it's a car. Long-term might be 20 to 40 years. If you're in the military and you're talking about something like an F-15, well, the USS Enterprise was 55 years old when they decommissioned it. B-52 bombers are older than I am. I mean, the kids that are flying these days have, they're so much younger than the airplane, it's not even funny. So whoever designs those things, you have to know some idea of how long you think your product's going to live, and it will be reflected in the design itself. Should you fail to reflect it in your design, you have failed as a designer, is the claim that I'm making. So in our industry, we worry about things like aging of the silicon, margins in the chip, and how do those shift with time. Thresholds can shift with temperature and time. We worry about so alpha particle hits, we talked about that. This idea of using commercial silicon in safety critical applications, that is happening more and more often nowadays because the capability of commercial stuff is so good and the cost is so good. But there is a difference. The same thing when I made fun of the Air Force general who wants, smart app software. He doesn't really want that, but he thinks he does. There is a huge difference between the way one engineers a safety critical system and the way one engineers a commercial system. And I can tell you that as a commercial designer, that's just a fact. So when people start taking the commercial stuff and using it in the safety critical application, I say, be very careful with that. And that's what I think is not happening right now, especially with the self-driving cars. Here's another example. You know about the Kata airbag canisters? You guys know about this? You've got them in your cars. So if your car is relatively new, you're probably okay. But as it goes along, a bad thing can happen. So here's a Takata canister. Not actual size, they're small. But the way they work is they combine some chemicals together to produce a heck of a lot of nitrogen in a hurry. So it's kind of a controlled explosion. The problem is if that canister, this metal canister, if anything were to happen to it, like corrosion or whatever, or if the chemicals have destabilized and produce nitrogen faster than expected, it can throw fragments of that can right at you as the person sitting there, and that does not do you any good at all. So that's a problem that the auto industry is currently grappling with even as we speak. And all of our cars have these in them. So my point is these things worked really well on day one of production, but as time went on, we have discovered that not all of them age gracefully, and that's a problem. Another one, DC-10s are airplanes, big cargo airplanes. Well, they used to be passenger planes too, but they decommissioned them after a series of bad things happening. One of the things was, if you actually look at there's a cargo door in the back underneath the fuselage. And when you're in one of these airplanes, if you haven't thought about it, they're pressurized, otherwise you wouldn't be breathing as well. And that means that they're pushing out on the skin of the plane, because you're up at 35,000 feet, the air's pretty thin. So it's pushing out, and the differential of pressure is pretty high. Well, the DC-10 designer, for some reason, decided to open the door out because it gave better access to the cargo bay. The problem with that is the pressure's pushing it in that direction. So all the other makers, including when you walk onto an airplane, take a look at the door. The door swings in and then pushes out against the frame of the plane. So the pressure helps hold it closed. And that's why some crazed passenger who tried to do this just the other day can't walk up in flight and grab that handle and open the door. It won't open because the pressure's working against them. But for some reason, the DC-10 guys did it the other way, and they had a case where the door wasn't quite closed. And of course, when's that going to manifest? If you're going to have a problem with that, it's going to manifest when you're up at altitude, where the difference is the biggest, which is exactly what it did. So they went up, the door blew out, it collapsed the floor, and it wiped out all the redundant control wires out to the tail. So it's another example of one thing affecting what you thought were redundant control, but they weren't. It turned out not to be redundant because of the implementation of the idea. How about putting a backup generator too close to the ocean? Can you think of any examples of that? Yeah, I'm talking about you, Fukushima. I mean, on the one hand, having a nuclear accident accidents are normal. Read Charles Perrow's book if you don't believe me. I think he wrote a book called Normal Accidents, which I highly recommend. He's a sociologist that took on the question of, if you're going to design complicated things, they seem to fail. And when they do, they fail in characteristic patterns. Can we learn anything about those patterns? Would they tell us anything as technologists and as designers? And he concluded, yes, they would, if we pay attention to what the lessons are. This would not have exceeded his threshold. He would have just said, this is obvious. Don't put your backup generator too close to the ocean. There was a guy named Hyman Rickover in the US Navy. He's the one that got us into the nuclear Navy. He was either loved or reviled by the sailors under him, because he was an incredibly harsh taskmaster in terms of nuclear technology. He knew how serious and dangerous it could be. So he handpicked all of the lieutenants on his submarines that were going to be nuclear capable. And he apparently was seemingly fairly capricious about who got in, who didn't. I was telling my boss at Intel once, reading this book about Hyman Rickover, walking off the plane in San Jose. And I was just saying, and I'm reading this book, and it's talking about Hyman Rickover, about how he was such a finicky guy about who got into his programs, and how that turned out, some people got really mad at him. Their whole careers, they just hated the guy. But he was a very effective guy, because he was one of the people that said, you know what? Commercial plants should not be next to cities. They should certainly not be in cities. Because no matter how careful we are, no matter how much training we do, worst case, the physics of the situation is that that's a disaster. That's a dangerous thing to be sitting there. And we should therefore, just for that reason alone, move it far away from a city. And by far away, he meant like 100 miles. So he for the first, I don't really know how many, but for the first set of commercial nuclear reactors in the US, his influence caused them not to be situated in major cities. After a while, it was all bets are off, and he wasn't part of the decision process anymore. Anyway, let's see. So user interface is another thing I like to pick on, because I think it's a common cause of a lot of the problems we face with our technology. There is a ferry. Well, if you're the captain of that ferry, you need to know if the loading doors are closed before you cruise away from the dock, because otherwise you don't actually have a boat. You have something that's more like a submarine. And the problem is, in this one specific instance, the guy forgot to close the doors. Another problem is there's no indicator on your dashboard as the captain. It doesn't say doors are closed or open. Why is that a good design decision? I don't know, but this is what happened. The boat ended up sort of flipping over. And so you look at that and go, come on. Sometimes user interfaces are really hard to do, but not this time. This is pretty obvious that something was necessary that wasn't there. Come on, this is the bonehead one, right? I don't like bonehead ones. I think we should avoid them. Here's another one that's you can decide for yourself which one you think it is. In 1988, the USS Vincennes shot down an Iranian commercial airliner, and a lot of people died. The US Navy spent a lot of time and effort to figure out what happened. And in effect, what happened was there was a single Navy operator of this complicated system called Aegis, which we still have, by the way. We still use it. It's just an evolved version of the same thing he had. But the problem that he had was he had a big screen, and it was showing lots of traffic, all sort of, and his job was to watch, is anything coming towards my ship? Because if it is, it could be a threat. And if it's a threat, I have to do something about it. And they were on heightened alert anyway, because there were lots of heightened tensions at the time and so on. Well, this guy, his display was not sufficiently capable to show him everything he wanted to see. So he could see where the Vincennes was, but he wasn't sure that's what it was. Sorry, not the Vincennes, the airliner. But he wasn't sure if that was a commercial airliner, which he knew was up there, or an enemy fighter, for instance. Worse than that, because the system just wasn't capable of differentiating, but worse than that, the system was set up such that he had to, if he wanted to know what that thing was doing, he had to run the system multiple times and do the differentiation in his head. Oh, wait a minute, if it was there last time and here this time, then it must be going that way, which means it's not aimed at me. And he used to do all of this thinking that he's under an existential threat to him and his entire ship, who's counting on him to keep them alive. So he was under a lot of duress, a lot of pressure. And in the end, what happened was he mistook the thing on his screen as being an enemy fighter, essentially, because he was listening to the communications coming from a parked F-14 somewhere else. And the system wasn't capable of differentiating that. He had no way of telling that that's what was happening. So he made the worst case assumption and took the worst case action based on it. And it's all because, I claim, the user interface of that system wasn't good enough to be part of what it was capable of doing. It was capable of taking down a commercial airliner. So when you've got the bar set that high, you better have the rest of the system commensurate with that, and it clearly wasn't. Here's some more. If you're a pilot, you look at a bank of dials like that, and you know what you're looking at. You've got gradations around the side, and you've got a big bar, and you can see where you are. Oh, the range is here, and the bar is here. I can see how I'm doing. And you can even do that when the plane's shaking, because they often do. You've been in turbulence, right? If you're the pilot and your plane's doing that, that's what it looks like to you, too. So those were the old analog dials. Well, we can't leave well enough alone, so we want to do digital dials. And so that's the digital equivalent of that same cockpit display. And here's the digital representations. And you can see they sort of got the half hemispherical thing going. They've got that. But where in the heck is the indicator that says where you'd like to be? Well, that's over here. It's this tiny little green light on the side. So if you're shaking, if the plane is shaking, you can't see it. And that's what happened in this case. The guy flying that plane went into turbulence, couldn't read the dials, and did the wrong thing with the plane. I want to get towards more robust hardware and software, no matter what it takes. So I'm taking into account the technology and the user interface. And I want to do it for immediate, long-term, and user interface, as I mentioned. I would claim that we already aren't good enough at ensuring that the systems work as specified. That's what we try to do. I don't think we're good enough at that. But I don't think that's enough. I think in the end, what you really want is the system to fulfill the intended mission. I think the specifications to say the intended mission is something specific, plus a bunch of caveats. That it should never run the user over a cliff. It should never shoot down a commercial airliner. It should protect the ship from certain classes of threats. And I want the system to measure its own output against those things as well as just live to the spec. Those are slightly different things. I think we're setting the bar too low, and we're not hitting it already. Remember Star Trek from the 60s? If you were sick in 1965 in Star Trek, you went to the sick bay, and they put you on this machine, and it would show you. In fact, I could still hear those weird sound effects that went with this picture. It was just like weird bleeps and bells noises. But here's the thing. They showed ranges for various parts of your body. Lungs, this is lungs, brain, cell rate, whatever that is, blood. And they made them up, of course. But the idea is whatever you might want to measure about a human body, well, here's the entire range it could ever have. Here's the range you want, and here's where you are. Just at a glance, you can see how you're doing. It's actually a pretty beautiful display, I would say. I want that. When I walk onto a commercial airliner, I want that display in front of me. Here's how the nav system's doing. Here's how the GPS is doing. Here's how the pilot's doing. I want to be able to look at that and go, yeah, everything's nominal. By the way, one thing I don't see on here is trends. Like maybe if I see something like, okay, look at this one. Here's the green bar, and it's up a little bit above that. And you might say, well, is that a problem or not? Oh, I don't know. Which way is it trending? If it's trending back towards green, maybe it's okay. What if it's trending the other way? then it's probably a problem. So I need to know I want to know the current status. I also want to know the trends. So I think that is a whole lot better than like service engine soon, like on our cars. I hate that. That's ridiculous. And I think it's partly because the guys who design cars just don't know what to do. The people that drive the cars are not technical. Have you ever been in a cab in New York City that did not have that light on? I don't think I ever have. They seem to think it needs to be on or you can't drive. I don't know what it is. But it certainly does not fulfill what the guy who designed this thing intended. That was, he or she did not want you to keep driving indefinitely after that lights. But you know, if the car still seems to work, naive people are going to go, hey, so far so good. Maybe the light's broken. Yeah, maybe. So anyway, what I would like is I want complex systems to tell me how they're doing in terms of their nominal expected range and the trends that they're exhibiting. And then I'll have some sense for whether I can use this thing or not. At DARPA, they always want to do exoskeletons. Like in the movie Alien, Sigourney Weaver strapped on this exoskeleton and she could take on the alien. That might be an extreme case, but the Army wants to put an exoskeleton on their soldiers so that they can carry those crazy heavy packs like they always take into battle. And they want to be able to carry a lot more stuff and so on. And at one point, I heard this pitch so many times I can't tell you, but at least one of them, I said, well, wait a minute. You know, if I'm a soldier and I'm about to strap one of these things on and march down the road for 10 miles and then go into battle, I want to know what the real status of that thing is. Because I want to make sure it's not in the form where it will get me the 10 miles and not be able to get me back, for example. Or maybe I'll switch it for another one if it's not quite up to the task. But I don't want it just like a battery okay light. I want to know, you know, am I getting the torque out of the motors I'm supposed to get? Is the battery life, you know, as good as it's supposed to be? Is this thing safe to take out? In some funny use of the word safe. When I wrote this all down, I thought, well, this might seem obvious to you. You know, maybe this just seems obvious. But if it is, remember the guys who designed the DC-10 cargo bay didn't get it. The ferry door guys didn't get it. The airbag cartridges in your car should not be failing this fast. It's maybe not as easy as it looks. So and I only see this as a partial solution. I'm not claiming this just fixes the user interface problem. I'm just saying it's an idea. I think it pushes us towards a user-machine interface that is more reliable and workable than the ones we've come up with so far. Because the ones we've come up with so far have some real issues with them, I think. Oh, and then of course, I mentioned this earlier, it has to be non-spoofable, non-hackable. That new requirement is absolute, because people will attack it. I don't know why they do it, but they do. All right, so there's some lessons from the DoD that I also thought were fun. The F-15 is a heck of a good airplane, but it's getting old. It's like 40 years old now. And it's got chips in it. It's got lots of silicon. It doesn't have that much software because it was designed so far back that software hadn't been invented. I'm just kidding. But there wasn't much. But it does have a lot of chips. And those chips fail, and when they do, they've got to replace them to keep the airplane in service and so on. So they've got this logistics tail. And this is true of pretty much everything in the armament of the US military. And the F-15 is just one of the older airplanes to suffer from this. By the way, the B-52s that I mentioned earlier, those hardly have any hardware or software in them because they were designed in, late 40s? So they're pretty simple. Now, they've been retrofitted. They do have radios. They do have, entertainment systems. No, just kidding. They do have some stuff in them, but it's not as elaborate. It's like if you look at an F-22 or an F-35, those are amazing. We're going to get to that in a minute. But you also have to maintain all that stuff, and that's where a huge fraction of the cost of those systems comes from, was because you've got to keep working on them long past the date when they were first hit the market. There's also this issue of untrusted foundries. Have you guys thought about that? So from the DoD's perspective, it was a brave act to go off and start buying commercial silicon, because there was a time when the Department of Defense in the US designed most of its own stuff. And it was like so much better than the commercial guys could do. Yeah, it was expensive, but so what? And it was a beautiful thing from the DoD's perspective. Nowadays, it's reversed. And like FPGAs, for instance, the microprocessors, the DSPs, all that stuff right off the shelf is way better than what the military could do if they started from scratch, and in the amount of time and money that they have. So they buy it. But when they buy it, they now are exposed to some problems they just never really thought about and don't have a great answer for yet. The foundries, and so even as recently as, say, 7 years ago, IBM's fab was so-called trusted fab here in the US, and they could get IBM to make the chips that the military wanted. IBM's not in the business anymore. So now they've got to go to other countries like, say, I don't know, Singapore, Thailand, China, there's lots of places where did I say Taiwan? There's lots of places they've got to go to get these chips that aren't in this country. And the question is, could a bad guy potentially use that access to silicon that's going to end up in our systems to do harm to us? And if you can't prove to yourself the answer is no, then it's a concern. That's the way the military looks at it. So that's a problem. And are we designing accordingly knowing this? And the answer is not really, because we don't know how to do it yet. So here's another issue. People have said, for example, in the F-35, it's late, it's incredibly expensive, and people have said, oh, it's the software. When I was at DARPA, I said, well, okay, let me check that. I want to see what that really means. What's it mean to have software that's too expensive? First of all, how much is there? So when I started checking this down, I ran across the Air Force general in charge, is a guy named Bogdan, General Bogdan. And he says, the F-35 is a flying software computer. I'm not quite sure what that means, but it sounded like a cool phrase, so I kind of liked it. But what he's trying to say is, software is my bugaboo. Software is my thing that's killing me. What do I do? He considered it a huge risk, and he says, we got to fix that. We got to do something. Here, he was quoted as saying there's 24 million lines of code in that F-35. I found the Lockheed manager who's in charge of this stuff, and he says, no, that's like if you add the lines of code in the MP3 player of your dash to the lines of code in your engine controller. You wouldn't do that. That doesn't make any sense. But if you did, you'd end up with a big number like that. He said, if you want a number of the lines of code that is the problem that Bogdan's talking about, it's closer to 9 million, which is still a big number, but it's not 24. So there's a picture of the plane, and there's the 9 million lines of code. And otherwise, so then I said to this software manager, people are blaming essentially you for the overage of this airplane. You know, how do you plead? And he said, well, yes and no. He said, for the task I'm being asked to do with the amount of code that is needed to do it, yes, we're late. But in effect, it's not the number of lines of code that's the problem. It's the complexity that those lines of code represent. That's the problem. You're asking us to do incredibly complicated things inside this airplane. I was mentioning last night to Louise, for example, the helmet that those guys wear in an F-35, they can put it in a mode where if they turn their head sideways, they can see through the skin of the airplane because there's a camera over there, and it switches to that camera. They can look down and look through their feet and see what's underneath them because there's a camera down there. Same one above their head, one pointing backwards, one pointing out. So no matter where they look, they can see outside their airplane because of a camera, and the image is projected inside of their helmet. That's an amazing technical achievement. It costs like $900,000 per helmet. But you know, as a techie, I just go, whoa, that's so cool. And maybe they can drive the price down. I don't know. But the issue is that's one example. That's just one example of what's inside that airplane in terms of complexity. They have other ones that cause the planes to communicate with each other and synchronize on a really tight basis. And that's also really hard to do and to maintain and to sort of take advantage of. It gives you really good operational advantages when you can do it, but it's really painful to get it right. And so these guys, they're suffering. And so I thought it was important to draw attention to the fact that sheer amount of code isn't really the issue. The issue is that people are conceiving really complicated systems. Where would you implement those complicated systems? You put them in the software. So the point being that languages and tools and compilers and programming environments, if complexity is what's killing you, those aren't necessarily the right answer. If it really was just a software issue, then you could think about training and tools and languages, and maybe it would really help. So the point is we have to narrow that down. We have to figure out what we're really up against before we know how to attack it. Then I think there's also the impact of the end of Moore's Law. It's just for calibration. I think Moore's Law is going to end somewhere around the 7 nanometers, and you could maybe talk me into 5, depending on your definition of end. But I don't think it's going to go much beyond that, and I don't think you'd want it to if you could, because the transistors, there may be more of them, but they're not any good. They're not any faster. They burn too much power. You can't turn them on. There's a lot of problems with them. So we're looking at other paradigms, as we should, and you guys are doing this as well. I think that's great. We look at approximate computing. We look at neuro. We've got quantum. We've got, you know, there's some other things that are worth exploring now that the easy and cheap oil has been dug out of the ground. And I also think I'm somewhat intrigued by the idea that I think we're going to re-need numerical analysts. There was a time when you had to have, if you were a serious computing company, you needed to have a person who called him or herself a numerical analyst. And they could tell you about the stability of your algorithm. They could tell you how many bits of precision you needed to have a reliable answer and so on. When floating point, when IEEE standard came along, we all got really kind of fat, dumb, and lazy, I think. And we said, you know, try single precision. If that doesn't work, try double. It'll probably be good enough. And that has been how our entire industry has been working for 30 or 40 years. But when we start doing things like approximate computing, we're going to have to revisit the question of, is this stable? Is this answer reliable? Can I hang my hat on it, or do I need to try it again? Or, it's a question worth re-asking. The idea that Moore's law ending is going to level the playing field for the US military is a real issue. We have a high-tech military. We try to have an outsized influence on the world relative to the size of the number of people in the military. You might think the US military is really big and overfunded. We could argue about the overfunded, but really big is not compared to the rest of the world. We don't have nearly as many people under arms as the other countries, as many other countries. And the reason is because we're high-tech. We substitute technology for sheer numbers. We can do that as long as our technology is, in fact, better than everyone else's. If it isn't, suddenly our weakness is exposed again, the fact that we don't have as many people involved in this enterprise. And that's a problem. If you're thinking militarily, we could have a whole different discussion of whether that's the right way to think. So if Moore's law ends, you don't wait 2 years for a new system knowing that it's going to throw it out and get a new one anyway. Instead, it's like the B-52 thing. You better design knowing it's going to be around a really long time. What are you going to do differently knowing that? So we're not used to that. That's a game that none of us are used to. How do we fix it? Well, I think already designers should be trying to anticipate all of the different ways a machine or a system that they're designing can fail or be misused. And you could ask, well, wait a minute. Like in the example of the guy with the candle in the wall, is that even possible? Is that reasonable? And I think, well, maybe in any specific instance, maybe it's not reasonable, but the attitude needs to be there every single time. The attitude always has to be, I must try to anticipate every single thing that the bad guys might do or that nature might throw at me. And if I can do something about it, then I should try to do it. And if you don't ask that question, then you certainly will not. And that's why I think this is so important. The pernicious aspect of, I think we are all wired as human beings, and I think non-techies are even worse than techies, that if you avert a disaster, it doesn't get noticed. It does not have the impact. And that's a sad thing, because it means that we're only really going to learn from real disasters. And for every real disaster you see, there are 10x near misses. So you really don't want to be on the wrong side of that. I mentioned Charles Perrow's book. There's another book called Near Misses, and it's well worth reading. It's the one that establishes the 10x ratio, because it's harder. It's a lot harder to track down near misses. People don't want to talk about them. They don't really. A disaster you can't avoid. If an airplane falls down, you just can't deny it and say, whoops, I intended to do that. But if you've got a near miss, people are more than happy to sort of look the other way and say, whoa, I'm glad that's over. Let's talk about something else. So it's harder to learn from those, but it's even more important, my personal opinion. So as I mentioned, last time I was talking about this stuff, I was asked, who's going to pay for this? And surely that's going to be the problem with what you're suggesting, that we should all be designing for worst case scenarios and so on. And I thought about it and I said, well, that's a fair question. I do think there could be a cost to it, but not always. And here's an example. When I did the P6 at Intel from 1990 to 1995, in the first few weeks where we had the design team together, I realized that we're going to go out of order. It's going to be, for the time, a really complicated microengine. Complicated in my world means you're going to be exposed to the risk of bugs. So what are you going to do about it? So I said, you know what, let's compare notes. At the time, the three senior guys, me and two other people, we had designed some other things before. And I said, let's combine our knowledge here and experience and see if there's a commonality. So where do bugs come from? And so we went kind of around this loop of three people, and we realized the bugs that we had found in our past were always the same source. It was a complexity involved in taking a pipeline of things that are supposed to happen one after another and having something asynchronous injected from the side, like an interrupt or a trap or a fault or a breakpoint, anything like that. That configuration of events is what causes most of the really hard bugs. Like cache coherence bugs and floating point bugs are often another source of important bugs because the state space is so big. There's so many places for the bugs to hide, like the famous FDiv flaw from Pentium. There were just too many. The state space is what hid that bug. But in the case of in the case that we started working on the P6, I said, if there was a way to sort of tame that issue, where we have this standard pipeline where the data flows down and all this crazy stuff hitting it from the side, if there was a way to attack that problem, we'd be ahead of the game. Can we think of such a thing? If the answer is no, we're no worse off. But if there is a way, it'd be really cool. It turned out there is a way. And so what we noticed was In the front end of a P6 in any out-of-order engine, you're speculating. So you're going to stuff things into the pipeline that may turn out to be wrong later on. And you'd better have a really robust mechanism for detecting that case and recovering from it. That's just a mispredicted branch, right? That's all that is. And so you know you're going to take lots of those. They're routine. So whatever that robust, known to be robust mechanism is, if you could map all the other asynchronous garbage onto that mechanism, you'd be ruling out entire classes of bugs that otherwise you'd have to sort of try to avoid by thinking through all the possible corner cases, et cetera. So what we did was we literally overlaid the faults, traps, and interrupts and so on onto the branch mispredict mechanism, and we used the same mechanism to handle both. It worked great. It ruled out an entire class of potential bugs. It's not that we didn't have any bugs when we were finished. We didn't have those bugs. So it's an example of something that when we just thought about it, it made the machine better at no cost. And so I'm not saying everyone can do that, but you got to ask the question. That's all I'm saying right now. And if you don't believe me, here's Linus Torvalds, and he says, avoiding complexity reduces bugs. I rest my case. Linus said it. So. But even if it does cost money, suppose it costs money and you couldn't find a free way to do it, like the example I just gave. Well, fewer bugs still saves you money, and you don't know how much. Like the FDiv flaw was close to $500 million for Intel, for example. And fewer surprises might even save lives when you start using these chips in places like self-driving cars. So all I'm saying is I think you have to ask the right questions about the risks and the usage models, and then ask what about those in the face of people determined to do you harm. So I call that the right engineering, and that's what you have to do. In the past, I think hope is an example of a strategy we've used somewhat successfully, actually. I hope this is reliable. Let's find out. We've gotten away with that many times. I submit to you, a place like Intel, I was really surprised at one point when I went to the people in the fab and said, would you please show me the actual statistics of how reliable these machines are in the presence of, let's say, nominal power supply, nominal temperature. I will just give you any context you want that's reasonable, and then at least show me the statistics, how reliable is this silicon in those conditions. And I could not get that data, not as their chief architect, not as anyone. I could not get the data. I don't know if they have it to this day or whether they just didn't want to tell me. I don't know. So failing that, I said, well, look, okay, I'm in charge of designing chips where there's going to be a machine check architecture involved. There's going to be things like checking parity across buses. There's going to be error correction stuff in memory. There's lots of places where the machine could be detecting things that are going wrong and reporting it to some central facility, and we could use that knowledge to make a more reliable machine. I'm not saying never fails, but more reliable, right? But I need the statistics. I need to know what fails in order to know what to instrument. I could not get that data either. And Intel at the time believed that people like Dell and Compaq might have the data, but would never tell anyone else. So we as an industry, my takeaway is we as an industry are not doing the necessary soul searching and data collection required to do the system reliability analysis that I think is necessary to support the kinds of things we're doing with our products nowadays. And that's why I call it, a strategy of hope. So I think we either have to step up to this challenge or something bad's going to inevitably happen. The overreaction of the government normally is to pass onerous laws that aren't really well thought out to try to fix the problem, never have it happen again. Surely we can do better than that. I got to believe we can do better than that. I don't want to have that sort of default scenario play out. And I think it translates into we need some new ideas on system reliability. We can't just say, like, if you ask NASA and say, well, okay, I need a highly reliable system, what are we going to do? And they're going to say, hey, I have an idea, triple modular redundancy. Yeah, that's nice and that works, but in a commercial industry, it's a hard sell to tell people, I'm going to charge you for 3 chips to get the performance of 1. That's a hard sell. They don't want to do it. So I'm hoping there's some better way if we just look at it and ask that question. So I've got some conclusions. I do think we need to keep pushing CMOS up the hill. It's not done. I think it's approaching the end of the hill. I think we can see the crest of the hill from here, but we're not finished. So keep doing that. That's good. We're good at fast, cheap, and efficient, and we should keep doing that. That's required. It's not optional. But what I'm saying is there's not enough. That's all we work on, and it's not enough. I want to point that I didn't say anything about this yet today, and I just want to throw it out there. Parallel programming, as far as I'm concerned, isn't a solved problem. And yet we've gone wholeheartedly multi-core, for instance, because it was convenient for the people who owned the architectures to do that, not necessarily because the world was crying out for multi-cores. And I think in certain cases, for example, I think NVIDIA's CUDA environment and places like that for those kinds of workloads, hey, that's not too bad. I mean, it's got problems, but it's at least effective. But there's places, if I give you, 120 x86 cores and say, here, go do some general workload, how are you going to, you're going to try to map that by hand. And you probably won't be very efficient at it. I don't think we've solved that problem. By the way, I think whoever does solve it, if you really do solve it, that's going to be incredibly lucrative. You'll get on Bill Gates' Christmas list for that. And as I've mentioned 1,000 times today, and I think you picked up the thread, I hope, I think people are building what I call scary systems out of our stuff already. And so I would rather sort of meet them from behind with the right stuff rather than try to convince them not to do what they're doing. And I also think we have to start worrying about corner cases and use cases, not just now, not just day of production, but 20 years, 40 years out. We have to explicitly grapple with that because the end of Moore's law means that people are going to keep using what we create, not just replace it in the future, like we're used to them doing. And please don't make us wait for lawsuits and accidents. That's a crazy way to do business. I think we can do better. So I will leave you with a new word. Adelphobia means the fear of not being good enough. And I personally think that we ought to contract adelphobia in this computer industry because I think it will lead us towards better systems, and I think the world needs us to produce those. Thank you.
All right. We have a few minutes for questions for Bob. Yeah, I'll go back.
So the world, now we're doing self-driving cars, we're doing cars with touch screens where there used to be buttons and dials, and just stuff that on its face is stupid. And yet it seems to be popular and the industry's buying into it. Is it going to take like crashes and lawsuits to make anybody take this seriously?
Yeah, I don't know if it's cynical or realistic, but my kind of knee-jerk reaction to that question about is it going to take a disaster to make people sort of take notice, disasters certainly do have that effect. Can't argue that. The question is, how good are we at anticipating a disaster and forestalling it? I can think of some cases of that. For example, the hole in the ozone layer from 1972. Various different nations actually got together, believe it or not, and agreed with each other to get rid of Freon so that they could close the hole in the ozone layer, or at least not make it worse, before we all sort of exposed ourselves to incredible amounts of radiation from the sun. That actually worked, and it actually had the effect it was supposed to have. It was a miracle, and it was not a disaster. I think, but on the other hand, for example, climate change, I don't see that kind of cooperative spirit anymore or willingness to believe the science that's behind it. And so as far as I can tell, the default path is to have the waves come over our houses and just live, and not us, but our grandchildren are going to have to live with the consequences. So that's an example, I think, of a disaster is going to happen to get people's attention. I wish it weren't so. I wish we could look, just have reasonable discussions and say that it's worth this much money to prevent that catastrophe, all in favor. But I just don't see much of that kind of thinking going on anymore. So I fear that my reaction to your question is, I think disasters are pretty much going to be the default as the thing that causes change to happen. I wish it weren't true. I'm trying to prevent that with this talk, by the way. Yes, sir.
So you talk about this in kind of a general aspect of like getting the whole world to suddenly change their concepts, but at a micro level, have you met individuals that have influence, at least in their sphere, that you say, hey, this is a problem, can we work on it? And they go, yeah, and I actually have power and money to fix part of this sphere of influence I'm in. I mean, just kind of attacking the problem more bits and pieces versus everyone.
Yeah, I guess so the question is, have I run into individuals that actually have the power to sort of start making this change happen? I would say yes and no. For example, in the military, when I've talked to designers who work on actual avionics systems or airplanes and so on, they have resonated with the basic message that, for example, in their case, using commercial parts has good things, which is why they do it, and bad things that they might not realize are there, like who made this chip? Did they stick anything that you didn't know about in there? Even if they didn't, what's the reliability? Can you put people's lives based on that? They're pretty well aware of those issues. The real problem that they face is our system of procurement in the United States for the military has gotten so bizarre. One set of people writes what they call a specification or a requirement, and then that goes through one organization, one committee after another, until it finally ends up in some mutated form on the desk of somebody who actually can sign something and make money flow back and forth. And when that person does what they do, the people who buy the resulting systems had no say in what went into them. they are just stuck with some number of whatever that was. And there was no process by which one brain comprehended all the changes that went along down that chain. So what I'm saying to your question is, I can talk to anyone along that line and engage them on this, and they will agree with maybe not all of it, but at least some of the basic ideas. But how does that translate into the final system that the guy bought? That's totally nonlinear, and that I don't really know how to influence with the way systems are done today. Like the F-35, I really think at some point somebody needed to do what Kelly Johnson did on the SR-71 Blackbird. You know, the reconnaissance plane that went Mach 3.5. There was a guy that was just a dictator about how that airplane had to be. And it was wildly successful because of him. So Kelly Johnson was the chief designer, and I like to cite him because he once, for example, told a general, at first the generals in the Air Force said, that airplane's never going to work. We can't make something that goes that fast. And when he finally proved that you could, they switched hats and they said, oh, well, now that you have one that does that, I want to turn it into a fighter and a bomber and a reconnaissance plane. And so Kelly Johnson's the one that said, wait a minute, if you're going Mach 3.5 and you want to get into a dogfight with another fighter plane, it's going to take you 3 states in the United States to make a turn, to come back, going Mach 3.5. That's not a fighter. And by the way, if you want to drop bombs, it's going to make the plane so much heavier that you're going to be lower, in which case you're going to get hit by missiles coming up from the ground. This plane only makes sense as a reconnaissance platform that's well out of reach of everyone else. And he was the one that kept saying no, 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 no to the people who needed to hear it, so that the final thing actually did what he said it would do. I fear that our procurement system in the United States, at least in the military, has reached a point where there are no Kelly Johnsons able to say no and make it stick, in which case what you get is the result of committee after committee, and then you get a plane that is like the F-35, which is wildly expensive, wildly aggressive in terms of its design objectives, and it remains to be seen if we can actually put these things into production. So to me, the answer to your question is like, well, there's the commercial sphere and there's the military sphere. And I'm kind of saying, boy, the military sphere looks very scary, hard to influence here, because it's no one person causing it. It's the system that's causing it. In the commercial sphere, the reason I said, yeah, I think a disaster would cause a lot of minds to change pretty fast, because we're kind of cued into disasters. We kind of can't refute those. But until the disaster has incurred, then it's just an expense, potentially. You're asking for more money for the same thing is what a lot of people are going to see it as. And then it's a tough sell. So I haven't seen very many people in the commercial space that have the ability to sort of just make a decision. If I could just convince her, boom, this is done. If that person exists, I don't know. I've never met them.
Great. One quick question, then we. Okay.
So kind of segueing off of this, I think you're a little bit more optimistic than I am, especially in the commercial space about the future of these things. Because it seems like to me, the Dilbert comment you shared at the beginning was spot on, right? Like this is how in a lot of different sectors, including the financial industry, we get disasters because there's not the proper incentive structure. Do you have any reason for this optimism?
Yeah. Do you have a smartphone?
Like, okay, yeah, I mean, like it works most of the time, but it also like shouldn't save my life. Like, do you have any reason to believe that like self-driving cars aren't going to be a complete and total disaster at some point?
We've got a bunch of them out there already, and we kind of have this tendency to test our way into confidence. We often do that, and that's not always bad. Sometimes that's all you can do, and if you insisted on anything but that, you'd be stuck and never make any progress at anything. And so I admire their chutzpah, where they're willing to go out and do this. What I don't like as much is if, to the extent they're doing it based on naivete on their part, about what we're selling them. That's what worries me. I had a case where I did a consulting job for a company, a car company, and I was appalled to discover how little they understood about the silicon and software that they were creating or buying from people. They knew nothing about what it meant to stick a computer in the loop instead of what used to be physics, like a carburetor or a transmission. And I was scared to death. And in fact, at the end of the one meeting, I told the big boss about my concerns that he must not allow aftermarket controllers for the engine because it could make the car go the wrong direction. And he said, come on, it would not happen that if you want the car to go that way, it's going to go that way instead. One of his own junior engineers leaned forward and said, actually, sir, that's exactly what did happen during testing. And I went, oh my God. So during the break, I told this kid, that was beautiful, but you need a new job. Your career's toast. That's just how the world works. I'm sorry to tell you that. But anyway.
Let's think, Bob. There's a reception now, so please come talk to him, ask more questions.